Okay, so today I want to look at some example problems using Darboux Criterion, which we covered last time. So the first example is a proof. I'm not going to give the proof in full detail though, but it's sort of a nice result, which says that if f of x is monotone, meaning it is either essentially if how should I say this? If a is less than or equal to b, then f of a is less than or equal to f of b. Or so this would be monotone increasing, or you can have monotone decreasing, but it has to be one or the other for all points, right? So so it's not just saying that for any 2 points you can have one or the other. It's saying that f is either increasing or decreasing, not both. So if f is monotone, then f is Riemann integrable. And I should note that, I guess I should put x's and y's here. Right? But the idea is that essentially the idea is that monotone means that f is sort of either preserving or reversing order of your inputs. X or y, y or x. Okay, and so like I said, I'm not going to give the full proof, but the idea is that if your function is monotone, right, it's either going up or going down, and that allows you to identify on each subinterval of your partition, it allows you to identify where your min and your max are going to be, right? If your function's monotone increasing, then capital M sub I has to be on all the way on the right, and then little m sub I is going to be all the way on the left. And then when you look at sort of the difference between your upper and your lower sums, you can actually then you can take an upper bound for your delta xi terms, right? Every delta xi is less than or equal to the mesh of p, which is less than delta. And then you just have delta times a sum of like f of m sub I minus f of little m sub I, which is going to be sort of f at one endpoint minus f at the other endpoint. So you get sort of a telescoping effect, and so you get that the sum that u minus L essentially is going to be bounded by delta times f of b minus f of a. Something like that. And of course the scenario is different if it's decreasing, but the easiest way to deal with that in a proof would be to take, say, minus f of x. If f is monotone decreasing, then minus f is monotone increasing. And then you know, since R of AB is a vector space, if f is Riemann integral, then so is minus f, and vice versa. Okay, so that's the first example, and one sort of neat example of a function which, sort of a non-trivial example of a function which satisfies this, is given by is given piecewise like this. So this is going to be defined on the interval 0 to 1, and it's going to look like this. So this is defined on 0, 1, and it looks like this. So what this looks like on a graph is that you have let's say here's 1, here's 0, right? So you have the point 0, 0. At 1, you can see this is going to be the case where n equals 1. If x is between a half and 1, then x is equal to 1. So you have 1 here, and then all the way to a half, it's going to be equal to 1. But once you hit a half, then you're at n equals 2. Your value is going to be 1/2, and then you're going to go to a third, and then you sort of just keep dropping like that. Right? So this is monotone increasing, although it's not continuous, right? And so this result tells us that this function is Riemann integrable, and you can actually find by sort of breaking up the integral is going to be sort of the sums of these rectangles. You can actually find the value of the integral should be equal to pi squared over 6 minus 1. But I'm not going to go into the details of that. It's sort of a nice exercise. Okay. The next thing to do is we have this this result. If f is a continuous function on our interval ab, so we know from last time that if it's continuous, then it's Riemann integrable, but we're going to assume it's continuous for this result. And non-negative on AB, right? So it's not negative at any point on AB, right? If I pick an x in AB, then f of x is greater than or equal to 0. And there is some point in the interval such that it is positive, then the integral of f is positive. Right? So first I want to mention sort of why we have this continuity condition. Well, you can construct a function which sort of looks like this. Let's say it's equal to 0 everywhere except for some point. It's equal to like 1, right? This is Riemann integrable. It's not continuous, and its integral would be 0, even though it has this continuous, it has this positive point. But this is saying that if our function is continuous and there's a positive point, then the integral also has to be positive. So let's see roughly why this is true. Well, the idea is that we sort of want to let epsilon be something bigger than 0, but less than f of p. Okay. Then, so 0 is less than f of p minus epsilon. So the open I'm just going to say it like this. So now, by the definition of continuity, there is delta greater than 0, such that if x minus p is less than delta, then f of x minus f of p is less than epsilon. And this inequality actually implies that how should I say this? Okay, so this says that minus epsilon is less than f of x minus f of p. It's less than epsilon. And then I can add f of p to both sides, so you get f of p minus epsilon is less than f of x, which is less than f of p plus epsilon. And so we know that f of p minus epsilon is greater than 0. So f of x is greater than 0 for x minus p less than delta. So now the idea here is that you have sort of an interval. I guess this is a closed interval. You have an interval where f of x is positive, and this allows you to essentially say that therefore we can take a partition small enough to have essentially some interval which is contained in p minus delta, p plus delta. And thus the lowest value on this interval, right, is positive, because it's positive on this entire interval. So let me make sure that yeah, because it's continuous, it has to achieve its minimum in this closed interval, which is contained in this open interval where f of x is positive. So the minimum is in fact positive, and so the lower sum is positive. And then since L of fp is less than or equal to the Riemann integral of x, we are done. Okay, so I'm skipping a little bit of like technical detail, but you should get the general idea here that right, that since we have, the main thing is that our function is continuous, so that if the function is positive, then we must have some interval of positiveness, right? And that interval of positiveness sort of induces positive lower sums, right? Which are lower bounds for our integral. Okay. All right, the next thing now we will prove is that the absolute value of the integral of f of x is always less than or equal to the integral of the absolute value of f of x dx. And so this is sort of an analytic formulation of the triangle inequality, right? The triangle inequality says that if I take the absolute value of a sum, it's less than or equal to the sum of the absolute values. And of course, integrals are sort of analytic versions of sums. So the way we're going to approach this is by defining some auxiliary functions, f plus and f minus. So what are these functions? F plus is going to be equal to f of x if f of x is greater than or equal to 0, and 0 if f of x is less than 0. And similarly, f minus x is going to be negative f of x if f of x is negative, and 0 if f of x is greater than or equal to 0. So the key observations is that f of x is going to be equal to f plus of x minus f minus of x, right? The absolute value of f of x is going to be equal to f plus of x plus f minus of x. And right, so these are essentially just, you can prove this by sort of casework. So the idea of this f plus and f minus, right, if we take, for example, f of x equals x cubed, then f plus is going to be this portion of x cubed, and then it's going to be 0 over here. Similarly, f minus is going to be this portion of the curve, but it's going to be flipped to be positive, and then it's going to be 0 over here. So this is f minus of x. Okay? So notice that f plus and f minus are non-negative functions. So if we take their absolute values are equal to themselves. Okay. So the first result we're going to show is that if f is Riemann integrable, this was a really bad R. Okay. If f is Riemann integrable, then f plus, f minus, and the absolute value of f are Riemann integral. Okay. The idea here, it's kind of hard to state precisely, but it does use Darboux Criterion, which is why we're looking at this right now. The idea is to show that if you take the upper minus the lower sums for f plus and f minus, these must be less than or equal to the upper minus the lower sums for f. And of course, these, as we take our partitions to be smaller and smaller, are going to approach 0, so that forces these to go to 0. So I'm going to briefly show, sort of sketch why this is true. So let's consider we're working over some interval of our partition, right? So this is xi minus 1, this is xi, and let's suppose that our function looks something like this. Okay? Then we can identify our maximum and our minimum. Okay? So the overall contribution in u minus L is going to look like this. Right? It's going to be this length is our contribution of capital M sub I minus little m sub I. Now, so this is f of x. Now, let's do, I guess, separate colors would be the best thing to do here. F plus is going to look like this. So f plus has been drawn in red. Or I'll just write it over here. So f plus is in red, right? It's this non-negative portion of f. and then it's 0 over here where f of x is negative. And so little m sub I for the plus is going to be 0, whereas big M sub I for the plus is the same as the normal capital M sub I for f. And so the contribution for the upper minus lower sum is this distance here, which is, of course, less than or equal to the contribution for u minus L for f of x. Now if we look at the negative portion, f minus, it's going to look something like this. So it's going to be 0 right here, and then it's going to be this portion of the curve that's under the the x-axis and then flipped up. So this is f minus of x. This is going to be big M sub I minus, and then this is going to be little m sub I minus. So little m sub I minus is 0, and capital M sub I is going to be minus little m sub I, right? But then notice that this contribution, right? So it's not at the same height here, right? Or at least the way I've drawn it. But this contribution is the same as this portion here. So we can see that that is going to be less than or equal to the original contribution for f of x. And so there's sort of different cases. I didn't figure out a way to sort of write this generally, but you can sort of look at other graphical cases to convince yourself that no matter the situation, these contributions of u minus L are going to always be less than or equal to u minus L. And there are cases where it's equal to, but of course it doesn't matter because this is going to go to 0, right? So u minus L for f plus and f minus are also going to go to 0. So by Darboux, f plus and f minus are Riemann integrable. Now to finish, we claim that the absolute value of f is Riemann integrable, and that just follows from R of AB being a vector space. By vector space property. Okay. So the last thing to show is what we've set out to prove, that this generalized triangle inequality. So what we can do is we start with the left-hand side, so we have the integral of f of x dx. This is f of x is f plus minus f minus, so this is going to be the integral of f plus minus the integral of f minus. Okay, just substituting in f equals f plus minus f minus, and then using linearity of the integral. Okay, now we can use the standard triangle inequality, right? We have a sum of two things, so this is going to be less than or equal to the absolute value of the integral here and the integral here. Of course, there's a minus sign here, so you might think, okay, do we have to do something different? No, you can treat it as a plus, because you can think of it as like plus a negative, but then you take the absolute value of a negative, you get the positive. So we get this result here. And then, since f plus and f minus are non-negative, the integrals of f plus and f minus, I'm using commas here very economically, the integrals of non-negative functions have to be non-negative, right? And you can sort of argue that in a kind of similar way we did with the previous problem about if you have a continuous function with a positive value, then the integral is positive, right? Sort of the key thing was that the lower sum, we could find a positive lower sum. And here, of course, any lower sum is bounded below by 0, because you can't possibly, your infimums are always going to be non-negative if your function's non-negative. So by this property, right, if these integral values are non-negative, then they're equal to their own, to themselves. So we can drop the absolute values because we know that they're non-negative. And then we can combine these two integrals by linearity of the integral, and with the inside is, of course, the absolute value of f of x dx. And so we're done. Okay. So I think the next lecture is going to be the last one on integration. And we will talk about sort of, if you have two functions which are Riemann integrable, we will show that the product is Riemann integrable as well. Okay.